All right, so this is your promised story time. So this is a partially true story. You can figure out which parts are true and which aren't. So how many people here have heard the name David Hilbert? Okay, so Hilbert was a famous mathematician at the turn of the century, the 1900s. He trained generations of mathematicians. And one thing you hear his name used in reference to a lot was he came up with something that has been called Hilbert's problems. In the 1900s, he proposed a set of mathematical problems that he thought would be useful for mathematics to study over the next century. And he thought this would be kind of a good guiding principle for how mathematics could develop over the next 100 years. So he came up with a set of problems, and they're called Hilbert's problems, and there's 20-some of these. And some of them have been solved, some of them are unsolved today. A lot of them branched off into entire new areas of mathematics. Some of them ended up being very disturbing in their analysis. And so you can find a lot about Hilbert's problems. There's wiki pages on it and stuff like that. So Hilbert was this famous mathematician. All right, so the story goes that Hilbert eventually retired, got tired of mathematics, and decided he was going to open a hotel. So he opened a hotel. It was called Hilbert's Hotel. And, he had all these people who were students of his or students of his students, things like that. Everybody loved coming to town and staying at Hilbert's Hotel. So he built a small hotel. He had about 12 rooms, and it was always full. And people would come by and they'd want to stay, and they'd say, sorry, we're out of rooms. So did such a good business. He got lots of money. He expanded the hotel. And eventually the hotel grew to have 100 rooms. And those filled up very quickly, right? Because now it was a much fancier hotel. They had really good food, and people would come by to stay at Hilbert's Hotel, and they're like, "Sorry, there's no vacancy." Okay, we're in the not true part of the story now, by the way. So he expanded the hotel further as he made more money, and now it had 1 million rooms. Okay, and people started calling this Hilbert's Magnificent Hotel. But 1 million rooms only goes so far. And pretty quickly those were selling out too, and people would come to stay at Hilbert's Magnificent Hotel. Sorry, there's no room. Next vacancy is in 3 months, right? So got more money, raised the prices, lots of income coming in, kept adding on to this hotel, until eventually one day they added on so many rooms that this hotel had an infinite number of rooms. Okay, and this is when people started calling it Hilbert's Grand Hotel. So let's talk about what we mean by an infinite number of rooms. So every room has a door in the front, and it's a very linear hotel. The rooms are laid out side by side. Okay, so it's just, and the first room has a 1 on the door, and the second room has a 2, and a 3, and a 4. And by ... I mean that if I had the time, I could keep drawing this picture to show you what exactly this Grand Hotel looked like. When we say there's an infinite number of rooms, here's what it means. If you pick any positive integer that you can think of, there's a room with that number on the door, and there's rooms to the right of that. Okay, that's what we mean by infinite. We don't mean that there's a room with an infinity symbol on the door. All the rooms have integers on the door, but you pick the number 10,017,017, there's a room 10,017,017, and there's rooms to the right of that. Doesn't matter how big a number you pick, there's a room with that number, and there's more rooms than that. Okay, that's the nature of Hilbert's Grand Hotel. Got the idea? All right, so what happens? Hilbert's having a birthday, and everybody's excited about this, and they say, let's throw a party at Hilbert's Grand Hotel. So they send out invitations to everybody they can think of. And everybody's excited they're going to come to the hotel and stay for the weekend and have this great party. And an old colleague at a physics lab in Zurich is working on parallel universes and trying to prove that they exist, and inadvertently has a portal open to a parallel universe when he gets the invitation and reads it out loud. And the creatures in this parallel universe hear about this and say, oh, we're going to go to this party too, right? And they had a portal open to another parallel universe, and there were an infinite number of parallel universes that all heard about this invitation and all decided to come to Hilbert's Grand Hotel. So the night of the party, everybody starts showing up, and it's an infinite number of guests. And they all come crowding into the lobby, and they say, "We'd like a room." And the person who works the front desk is very skilled and very efficient, and starts handing out keys to rooms to these guests. And gets faster and faster at doing it, right? And so after about an hour, every guest has a room. Infinite number of guests, they each have a room. And nobody has to double up, okay? And it turns out every room in the hotel is filled, but nobody had to be turned away. Okay, so you've got this infinite number of rooms and an infinite number of guests. And to simplify things, we're going to label these rooms R1, R2, R3, R4, and we're going to label the guests, guest 1, guest 2, guest 3, guest 4. And the first guest who showed up got the key to room 1, the third guest got the room to room 3, and so on and so forth. Okay, so the hotel is completely filled up. Infinite number of rooms, infinite number of guests. Everyone's happy. Make sense so far? All right. Now there was one poor grad student who on their way to the hotel got a flat tire. And they found a gas station, but you know, the mechanic was on their way to the Grand Hotel also, so they had to come back and fix this person's car. So this student shows up about midnight, and the party's in full swing, everybody's celebrating and dancing. And the student goes into the office and says, "You know, I was one of Hilbert's first students. I would love a room at your hotel. I see the sign that says you're completely full. Is there any way you can give me a room?" And the front desk person says, "Sure, give me 1 second," and they reach under the desk and they hit a button and they hand the person the key and say, "Here you go, enjoy your stay." So first question, how did the front desk person find a room for this new guest when every room was occupied already? So think about this. How would you find space for one more guest, given that every room is full?
Not every room is full. It's being created as quickly as a person is coming in.
Every room is full and you're not allowed to make any new rooms. Although that would be a good solution. And you don't want anybody to double up. You don't want anybody to have to go home.
They kill off somebody.
And you don't want to kill off somebody.
Did he already have a room?
Nope.
Wouldn't you ask every guest to move one room to the right?
So what if you ask every guest to move one room to the right? So you hit this button under the table and it puts up a little light in each room and says, "Pardon the inconvenience, could you please move to the next room to your right?" And everybody picks up their bags and person in room 1 moves to 2 and person in 2 moves to 3. And that takes, you know, a few minutes. And room 1 is free now. And that's where the new guest gets to stay. So even though this set was completely accounted for, you could still put one more person in. So that's a little weird. And if another person shows up late, can you do that again? Yeah. You could do that 1,000,000 times. You could fit 1,000,000 more people in this hotel that's completely occupied. All right. Well, there's another hotel across town that's also a grand hotel with an infinite number of rooms. And it turns out a bunch of guests went to that hotel. But that's in the part of town where birthday cake is illegal. So there's no birthday cake. And they're kind of like, this party's kind of a drag, there's no cake. And somebody like says, "Well, I saw someone walking around the other side of town with cake." And they're like, "There's another hotel we forgot about." So you have an infinite number of guests on the other side of town who all get up and come over to Hilbert's Grand Hotel with birthday cake and go to the front desk and say, "We would all like rooms in your hotel. There's an infinite number of us. Can you fit us in?" And the front desk says, "Sure, give me a minute." Hits another magic button, starts handing out keys, "Enjoy your stay." How do you fit an infinite number of new guests into this room that's already completely filled? And without having to do them one at a time, because there's an infinite number, you'll never end up finishing in that case.
Infinite front desk service?
That would be nice.
You have to move everybody down an infinite number of rooms.
Infinite is not a number though. So this is one of the subtleties about infinity. right? That would mean moving them down a number of rooms bigger than any possible number. So let's have a series of late guests, and let me call them late 1, late 2, late 3, late 4. And we want to figure out how to get them rooms in the hotel. This is why I don't run a hotel. This happens all the time. All right, do you want to know the trick? All right. Take each guest and whatever room number they're in, have them move to the room with twice that number. So guest 1 moves to room 2, guest 2 moves to room 4, guest 3 moves to room 6, guest 4 moves to room 8. And they can do that because there's an infinite number of rooms. And after they've done that, all of the odd number rooms are free. And now, have each of the late guests go into the room that's twice their number minus 1. And everybody's got their own room. So what does this mean mathematically in terms of set theory? We could have R equals a set of rooms. We could have G equal a set of guests. We could have L equal a set of late guests. And in some sense, the size of the set of rooms, and I'm going to use these vertical bars again to mean the size of a set. And if this is a finite set, this just means how many things are in this set. So if this is a set ABC, the size of that set is 3, ABC. But when this is an infinite set, this is not a number, right? And it's not infinity, because infinity is not a number. But this is somehow how big that set is. It's really big, right? It's an infinite number of rooms. This is the size of that set R, and this is the size of the set G and the size of the set L. So when we took all the guests and we put them into individual rooms originally, what we basically showed was that the size of the set of rooms was the same as the size of the set of guests. Well, that's not surprising. They're both infinity. When a late guest showed up, and we still managed to fit everybody into the rooms, what we saw was that if we take the set of guests and we add one more thing into that set, which is this student who showed up after the flat tire, the size of that new set is the same as the size of the set of rooms. And the size of the set of the rooms is the same as the size of the original set G. So the bigness of this set G is the same as the bigness of the set G with something else added into it. And that's non-intuitive, right? If we just think of this as the number of things in the set, if we add something to the set, there's one more thing in the set. Can't have the same size. But when this is infinite, adding one more thing, it still has the same size. And when we added in all these late guests and we still managed to fit them into the room, what we see is that the size of the set of rooms is the same as the size of the set of guests, union the set of late guests. Right, G union L, which is the same as the size of the set of guests, which is the same as the size of the set of late guests. So two infinite sets union together, nothing in common, right? You should get something twice as big, but in fact they're the same size. Right? We just proved that with a funky hotel. So infinities are weird. In this notion of size, where we say two things are the same size if you can take everything in here and associate it with one thing over here uniquely, which is what you're doing when you're putting guests in rooms, if these things are infinite, sometimes you put two of them together and you don't get twice as much stuff, you get exactly the same amount of stuff. That's a little weird. It gets weirder really quickly. So the next town over has a hotel, and it's called Blauman's Magnificent Grand Hotel. And in Blauman's Hotel, the rooms are labeled with real numbers. They're all bigger than 0, but they're real numbers. So there's a room 1, a room 2, a room 3, but there's also a room 1.5 and a room 2.6 and a room 3.1, 2, 3, 4, 5, 6, 8. And for every real number, there's a room and vice versa. It's an infinite number of rooms, right? And that hotel is completely filled up. And there's so much noise coming from Hilbert's Hotel that the people figure out, hey, there's a party in the next town, and they all check out of this hotel and go over to Hilbert's Grand Hotel and come to the front desk and say, we would like rooms at your hotel, can you fit us in? And what does the desk clerk say? I'm sorry, there's not enough room for you. And it turns out there's no way that you can take this infinite number of guests and give them rooms in Hilbert's Hotel. And the reason is, if we label these guests, let me call it lowercase g 1.5 and g 3.1415 and so on, and let me call that set G, those are the guests from the next town, it turns out the size of that is fundamentally bigger than the size of the set of rooms. Well, since every room corresponds to a real number, and don't worry about negatives, it won't change anything, this is actually the size of the set of reals. And this is actually the size of the set of integers. And the reals are fundamentally larger than the integers. And we can prove that. We don't have time today, but it's a really simple proof. And it's a powerful proof, so we'll prove it sometime this quarter. But the set of even integers is exactly the same size as the set of all integers. The set of prime numbers is the same as the set of all integers. The set of integers that are a multiple of 1 billion has the same size as the set of all integers. But when you get to real numbers, that is somehow fundamentally bigger. The set of rational numbers, fractions, exactly the same size as the integers. That's another simple proof that we'll do another time. So if you had a hotel where the doors were labeled with fractions, you could take everybody from that hotel and fit them into Hilbert's Hotel. But this is interesting. The reals are somehow fundamentally bigger. And so you start studying different types of sets, reals and power sets and Cartesian products and so on. And here's what you discover. You got the reals, you got the integers, which is a sort of small infinity, and you've got the reals. And this is strictly bigger than the size of the integers. And the question is there some set whose infinite size is in between the integers and the reals? Is there a set that's bigger than the integers but smaller than the reals? And so far nobody has found one. Right? You might think that the reals between 0 and 1 would be smaller than the set of all reals, but it's not. It's exactly the same size as the set of all reals. In fact, the set of reals between 0 and 0.00001 is exactly the same size as the set of all reals. But the fractions is the same size as z. All right, so there's a hypothesis called the continuum hypothesis, which we just call CH, so we don't have to say continuum hypothesis. So CH says no. There's nothing in between here. If you have an infinite set that is bigger than the integers, it's at least as big as the reals. Right? Or if you like, the first set that's strictly bigger than the reals is strictly bigger than the integers is the reals. So continuum hypothesis says no, there's nothing in between. So here's the question for our last 3 minutes. Do you think the continuum hypothesis is true or false? Do you think there is a set whose size is in between the integers and the reals or not? So let's do a democratic system. Let's take a vote. How many people think that there is a set in between here? So let's do continuum hypothesis is true or false. So how many people think it's false and there is a set in between those? One. Just one? Two. Okay, you can split the prize money. Anybody else? All right, 2 votes for false. How many people think it's true? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So democratically, CH is true. What's the reality? If you voted for false, you are not wrong. If you voted for true, you are not wrong either. It turns out continuum hypothesis is neither true nor false. It's what's called undecidable. It does not have a truth value. It's a simple statement, right? We just explained it, plus, with some story details. It's a simple statement, but it cannot be proven to be true and it cannot be proven to be false. Which means you can never find a set that satisfies this, because that would prove it's true, right? But you can't come up with some kind of clever proof which says there is no such set, because that would prove it's false, right? Or the other way around. It's formally undecidable, and that fact has been proven, right? There is a mathematical proof which proves that CH cannot be proven to be true or false. So it's formally undecidable. And this is a problem if you love mathematics and philosophy and you think that their truths are out there and are provable. This is a statement that is neither true nor false. And that really kind of like rained on some people's parades. And this opens up a whole branch of philosophy and mathematics and computer science when we talk about undecidability. And there are very clever proofs. So if you want to lose a little bit of time over the weekend, look up Kurt Gödel. And Gödel was a little-known mathematician who presented a paper at a conference in the 30s that nobody paid much attention to at first, where he proved that there's no way to make a system of mathematics that is both completely consistent and complete enough that you can prove or disprove every theorem. You're either going to have propositions that cannot be decided, or if you add enough stuff so you can prove or disprove everything, you're going to introduce contradictions like Russell's paradox. There's no sweet spot in between, no matter how clever you are. And he proved this. And it was a paper that didn't get much notice until people started thinking about it and reading it, and then they were like, oh my gosh, right? This is a huge wrinkle. All right, so that's your weirdness for today, not on the exam, not on your homeworks, but something to think about. And it comes from something as innocuous as definition of sets and counting. All right, so have a fantastic weekend. I will see you on Monday.